I would like to introduce Dr. Peter Riddle, who is going to be the speaker of today's event. He is a researcher and management consultant with a doctoral degree in research and development for large strategic projects. He's going to talk more on what he does and how far he's come in his career.
Okay, so I took a doctoral degree in R&D or in as my thesis, and I started back in about 2011. I had some family, 2012, I had some family illness, so I took about a couple of years break, but I finished in 2020. And I did my doctoral dissertation in December 2020. Unfortunately, it was remote because of the pandemic, but I managed to complete the degree. Just recently, I've just come back from Trento from the R&D Management Conference. And while I studied for my doctoral degree, this conference that I attended in different cities throughout the world was very important to talk to other researchers, get ideas, and have a research community. So if you ever do a doctoral degree, it's kind of important to have a group of people that you can associate with. And that's kind of what we're doing right now in the IIBA local chapter. So just some background on my job and how I got to know the information that I have. SHRED is a program that the CRA runs that I'm not going to focus on specifically tonight, but it allows companies to get tax credits for experimental work. And for a large company, during the period of 2007 to 2019, I managed that program for them and got a government assistance, multi-million-dollar government assistance for the projects that they were working on. And those projects had to meet certain criteria. And that's how I've come to do a doctoral study, because I also had access to the data over 12 years. And that's allowed me to see the projects where I was really a bird's eye view of these projects. It allows me to see things differently. Once I had finished my work and I left that company, I was still working on the data and I was able to see things that I didn't see during my work. And I think it's very interesting when you can do a retrospective on your work. On a different presentation, perhaps, if somebody wants to grab me aside and ask how you get an MBA and a doctoral degree and get the company you work for to help you with it, I'll give you some tips on that. That could probably be a separate presentation. So I've written a number of papers that have been presented at these R&D management conferences, and they're all focused about R&D tax credits and R&D in business. And I got a lot of help from the Project Management Institute, where they had a colloquium in Oregon, and I've attended other colloquiums where you get other scholars helping you with your studies. If anybody is interested, Roll Roads has a DBA program. I'm not sure if SFU does. A DBA is a doctoral in business administration. It's a more business-focused degree, a doctoral degree than a PhD. I'll give you some appetizers from the conference. One of the things that I attended was called, and I'll just hold it to the screen here maybe, was an innovation, it's kind of going to be blurred, an innovation challenge. And governments are doing innovation challenges to give prizes for companies that can come up with solutions to either technological or social issues. And this is one thing that was covered in the conference, and there was a worksheet of how it could be managed through university. This might interest SFU. I'm not sure if you guys are involved in any of these types of challenges where there's government funding for prizes and helping your students understand how to work in that world. So that was one thing that I came away with. The other thing I came away with was a colleague that I know and that's helped me with my studies presented on the concept of dematerialization. I'm not saying that word very well, apologies. But what it basically means is many things that were physically tested before in the real world, especially in pharma and engineering, can now be tested virtually through simulations and computers. Now that's kind of happened for many years, but there are distinct phases in those projects where a company has to decide, can they test something virtually? Is there enough information known about the process they're trying to test, or do they still have to resort to physical tests? And when I attended the presentation of Jeremy, who's the colleague I told you about, he gave specific clients and cases that he's working on where they actually will go through a criteria to decide whether they can simulate a test, or whether they, this was in the engineering iron kind of business, and whether they could actually simulate it in a program. And there is a project management and a BA component of that that you might want to be aware of. So if anybody is interested in those two appetizers, let me know. I'm now going to move on to the main course of the presentation. So the whole point of tonight's session is, and stop me at any time if you have any questions. I'm open to any chat or questions. And if I may not be looking at the chat, if somebody wants to just let me know if there's a question and read it out, I'll answer it. So the whole idea is that many normal companies that don't have labs, don't have guys with, or ladies with white coats, are doing R&D, and they're doing experimental innovation, and it's probably happening in your workplace, and you may be aware of it or you may be not. And the problem is, in a laboratory, it's pretty clear that it's funded up front. There's all sorts of budgets and management for R&D. There's stage gate techniques, which says which projects should proceed, which should not. But in regular business, where the business for some reason has to do some experimental innovation, and I will get into the differences of that in a minute, it's not always clear. So I've taken 12 years of data from my former work, and I've been able to crunch that up and come to some conclusions. And I'll be reviewing those with you guys tonight. So definitions. Research and development is described as activities and processes that lead to new tangible or intangible assets. I guess the iPhone would be a great example of that. They're novel, creative, uncertain, and there's a systematic, transferable, and reproducible activities. So there's a specification for a product that comes out of that. We're not talking about that strict definition of research and development. We're really talking about experimental innovation, which is to look for new ideas, but don't assume that they will work. Instead, whenever you can, test them at small scale, put in place the systems to learn whether they actually work, and based on this, decide whether to scale them up or not. And I would suggest to you guys that you're probably working on projects where this happens. You might be involved in a proof of concept. You might be involved in some kind of pilot, but you might be involved in something where the technical teams that you're working with, especially in an agile environment, have worries that what they're trying to do technically won't work. And we'll get into that in a minute. So why is this important for you guys? Why should you care about experimental innovation? The reason you should care is project overruns or failures. So we know that time, cost, and scope and quality is the 4 important components of any project. And if you have experimental innovation in a project, you cannot manage it with Gantt charts. You cannot manage it with the normal, even with the agile techniques of planning, poker, or other things, because the problem is unknown. It can impact your home life if you're working excessive hours. I've witnessed this where people are working on experimental projects, but their managers don't realize the projects are experimental, and they're working all sorts of hours to try to make up for the fact the project isn't being managed correctly. It can have a health impact because you have a lack of control, because you're sucked into a journey and a course of action that you might not have anticipated. And there can also be organizational failure, loss of revenue, internal customer dissatisfaction. I'm not sure if there's some folks here from larger organizations, but larger organizations use a concept called a shared service organization or activity-based costing, where the users pay for the IT development. The problem is if there is an R&D or experimental innovative component to the project and it slows up the project, the internal users keep paying, but they may not realize the risk, or the risk may not have been explained to them, because they're paying for the project as a business as usual project, and it has this hidden experimental component, and it gets out of hand because the customers keep paying, and then eventually they say the project is not complete. Why is that? And also loss of competitive advantage. If companies aren't experimentally development their legacy systems, their existing systems, if they're not competing in the marketplace, then they become less competitive against their competitors. Any questions so far? Okay. So the technological, these are the components of experimental innovation. So any innovative project that you're working on has a technological objective. This is what the BABOK says about non-functional requirements. And it seems to me, from my experience when I worked on very large projects, that these get stuck on a spreadsheet at the back of the BRD, or they're not given the concern. But these are normal things that every system has to do. And there are, certainly TOGAF and other acronyms out there to explain why a system has to be compatible, compliant, and so forth. But quite often, there is doubt whether a system can do the performance that it's required, whether it can be secure enough. There is technological doubt, and I'll get into the difference. So if we go to the next page, it can also be an architecture. It doesn't, just going back to that previous page, these are all hardware related. But just imagine if you define a rules-based system that allows users to define their own functionality, then the non-functional requirements of running that rules-based system fast enough. If the rules-based system takes 5 minutes to give a result, where a compiled program in a previous rendition of the system gave a result in seconds, then obviously it's not good enough. You have to find a way to technologically make the rules run really fast. This is a simple example, but not a bad one, and one I'm going to stick through the presentation. So imagine then this rules-based system, it has to replace the compiled programs. How to make a rule run as fast as a compiled program. And that is a technological uncertainty. So the objective, the technological objective, is to do away with all the programming and to make an open-ended system. And the technological uncertainty is, can that open-ended system run fast enough to satisfy the user requirement? And you can actually, quite often in R&D tax credit claims, it's good to come up with numbers. You can put this in microseconds or nanoseconds, or you can put some measure of how fast the transaction journey through the system, through the path, has to take. So the other point is, experimental innovation is not a learning exercise. You have to know how to program. It's not learning, picking up a programming manual and learning. That's not experimentation. So you have to have a current capability, a knowledge base. But that standard practice knowledge base that you have won't overcome the technological objective. It won't allow you to solve the problem. And the other key point I want to make tonight is that technological capability doesn't equal technical skills. You can have all the technical skills in the world, but still not be able to figure out how to overcome a technological uncertainty. So we've got the technological objective. We've talked about the uncertainties. And then on this rules-based system that we want to build, and I've got a little spelling mistake there, I'm sorry. Will it provide the speed to run as a compiled program? And basically, the constraints have to work in the organization. So if you come up with a solution where you have to rebuild all of your existing systems, that's not practical. So any experimental innovation that you work on, is constrained by your environment. You don't have to find a solution that is in the world a brand new solution. You have to find a solution that works within the constraints. And most large insurance companies, banks, governmental organizations have constraints because they have massive fleets of mainframes that they're not going to get rid of anytime soon. And any new system has to work within the constraint of those legacy systems. And legacy may not only be a mainframe, it may be an older version of a cloud service that's been around for 5 years. So legacy changes all the time. So systematic experimental work, and now I'm getting to the heart of this presentation tonight. Abduction is the process of forming an explanatory hypothesis. So basically, this is a very fleeting point in a project where somebody says, you know, if I used cache in a unique way, and if I use service-oriented programs in a unique way, and if I broke the rules up to several multiprocessors that nobody else has done before because our code is legacy and no one's tried that, it might work. So all of a sudden you have a hypothesis and somebody else may come up with another hypothesis. A good test to know you're in experimental innovation mode is where somebody in your team says, that will never work. Because if an experienced peer says, I have a doubt that your idea is going to work, then it is uncertain. And that's called the peer test to actually determine whether you're in an area where you're going to have to do experimental work. So abduction is the point of bringing a new hypothesis. Deduction is built in that as a test system. So abduction, you could have hypotheses, they could come up in a day, but it could take you 6 months, a year, 2 years, 3 years to build a full system that would do it to scale, which is why it's very important with the definition we got earlier that you must test things at low scale if at all possible. And I'll give you some examples where one project was built to scale and it had issues. So induction then is looking at the results of the tests and saying my hypothesis worked. And this is really a scientific method: abduction, deduction, and induction. And I'm sure you guys do this all the time. You might say, I have an idea that this will work. And then you spend some time building something that will test the idea. And then you look back at your work and you say, oh, that was a total failure. But I learned something from that. And that is the abductive, deductive, and inductive cycle that I've been talking about in the promo for tonight's session. So I collected data from 12 years because I was the tax credit manager for a large company and basically interviewed a lot of project teams and made claims to the government. And the CRA came along and said, yeah, this is R&D. And there is a definition of R&D in something called the Frascati Accord, which defines what's R&D is not. And the CRA uses that to dish out money. And in the chat session, I'm interested to find out if anybody has been involved in those government funding programs. So all this data got collected. And I then went and found in the literature that large firms do include R&D tax credits, and that I decided to try to use the data, and I got permission to anonymize and use this data over 12 years. So the research gap that I studied in my thesis was I had quantitative timesheet data because every programmer that was on projects that was R&D and not R&D. So just going back to this diagram here, sorry, this was a manual process to go through all of the projects in the company and decide which ones were R&D and which ones were not. And there were 4 populations. If you look on the right side of this diagram, there were 4 populations built. Most of the projects were business as usual. They did not have experimental innovation. 133 of the projects were very close, but when they were examined in detail, they were candidates, but they were rejected because they didn't quite measure up to the test of experimental innovation. And 257 projects were claimed successfully under the R&D tax credit program and were valid R&D, experimental innovation, and a business contact. And we had to exclude some because there was kind of some overlap. So those timesheets where the data was collected had 4 main phases: plan, design, build, and test. And I was able to map those phases to the text descriptions that described what the R&D was. And in a minute, and I used a system called compositional data analysis, where I took all the data and I broke down the design, plan, test, and build. And if you look at this diagram, and it's a Euclidean concept of compositional data analysis, it's geometric. You'll see the blue ones are the candidate projects. And the candidate projects that were thought to be R&D, but were found not to be R&D, had little test compared to the ones that were R&D and the business as usual. And one of the problems is R&D projects in a business environment look very much like regular projects, but the ones that we rejected as candidates had little test. So one hallmark of an experimental innovative project is if you're doing a lot of testing and you're doing rapid testing for technological reasons, not for user requirements, then the chances are you're going to have a project that has got experimental innovation. And I use this method to quantify it. And I took the timesheets and I took the project descriptions and I crunched them into a database. I wrote in a language called R. I don't know if anybody has used that. It's a statistical type language for crunching data. And I learned a lot. And I actually took a whole online program from the University of Girona in Spain. These are the 4 populations I talked about. And there is a definite difference between the ones that were candidates that were found not to be R&D, because they only had about 12% test components. So if you ever wonder, am I on a project that is experimental? If a lot of testing is going on and you're learning new things from the testing, the chances are it is. If there's little testing, the chances are the project is a BAU project that can be built from specification. I'm not going to get into that diagram too much. Obviously, my research project was complicated, had a lot of variables. Some of you in stats might have heard of MANOVA, which is a multi-variable kind of analysis. And I did a fair bit of that on the quantitative side. I don't recommend anybody who does a mixed methods approach if they do a dissertation. Mixed methods means you're both doing a quantitative and a qualitative definition. And there are various places in large organizations where there's the front end that faces the customer. There's the back end, there's the middle place, which does the batch overruns, especially for banks and insurance companies, and also government resources. And I was able to take a lot of those variables and study the effect of the R&D projects. This is a word map from a program I use called Atlas. And this was an analysis of the main project that was a big back-end project to do the overnight processes for this company. And this is a word cloud. And the significance of the bigger word in the middle is that that might have been there 50 times. So obviously, statistically, performance was very important to this project. A rule set is in there somewhere. And so there was a lot going on in this project in regarding performance, which is a non-functional requirement, which is a technological objective. This is an analysis of the timesheets mapped to the hypothesis. And what I've been able to do is, this project had problems. And I think the reason this project had problems is they didn't start with the abductive phase. They just started building stuff. And the abductive phase came later on, several years later into the project, when they realized that things weren't working as they would want. But by that time, they were way into the project. And you can see these are the plan, build, design, and test phases in those different colored lines at the bottom. And you can see definite shifts in the when they're trying to build new hypotheses and solve the problem. This was a very big project. It involved hundreds of programmers, but you would see these same cycles of plan, design, build, and test. And I can map that to the abductive, deductive, and inductive phases that I talked about. So I'm nearly coming to the end now. The findings are that a lot of large companies are doing R&D in COBOL. That may shock some of you, but it's not just cutting edge languages like the Django, the other internet languages that are out there. Many large companies are still trying to figure out how to make their mainframes work faster and more efficient and communicate with a wider variety of systems. So the pattern that emerged from this research is plan, design, build, and test phases can be triangulated to the written descriptions that I had of the projects. And if in writing they said, I'm testing this phase, I can see the resource effort for testing. I had to map certain job roles because it wasn't originally broken up into plan, build, design, and test. So I was able to take analysts, business analysts, and put them in the design or the plan camp, and then programmers in the build and testers in the test one. So there's a contribution here. There's a framework to study projects in large companies and to try to find out what projects are normal and what projects are not. So the fear is that I'm espousing to you tonight about abduction, deduction, and induction are from 12 years of data and so forth program. And it's good to have tools that can really take apart if a company is really doing valid R&D. A lot of small companies don't keep timesheets, and that is a challenge. In this case, I had a large timesheet database to look at. So the scientific method that I've espoused today by Charles Sanders Peirce, who's a philosopher from about 100 years back, about abduction, deduction, induction. Abduction is you have an idea. Deduction is you build that idea out into a test framework. And induction is you observe the results. If you see those patterns and you're in a project, the chances are you're in an experimental innovation project. So that is a way to understand if you're actually in a normal project where you're just building stuff and it works first time or has some coding problems. But if you're in an experimental project and people are saying, oh, I need a new hypothesis to figure this out, then you better check yourself because you're not in a normal project anymore. And you've got to manage that or interface with the people managing that project in a different way. I know you guys are BAs and not PMs, but it's still important you have a huge influence on a project. And it's still important to understand if you're in a project that is not normal and is an experimental project, you need to know that and be able to recognize the signs. So there's some sources that I've quoted tonight, my main sources. I met Ian Miles at Manchester University, and he was doing sectorial large studies. And what I've done with my study is I've got under the covers into the project level. And these are some of the papers that I've presented at various conferences. Now, right now, I'm working for a company called I'm in Canada, where I'm doing consulting on R&D. And helping companies with innovation funding and credits. And my job is to analyze whether a project is R&D or not. And I've worked on some very interesting projects recently, taking Amazon Cloud Services and repositioning it in a new way for real-time processing, taking some open source software and allowing the user to design documents through an interface. And quite a few other things like that. So I'm not only sort of doing the research, I'm in the swimming pool, swimming with the problems and trying to figure out in a business setting, when is a project experimental and it's left the domain of a normal project. And I'm done.